Lagrangian of a double pendulum. So we've got the following pendulum shown in a figure where we've got a truss of length L1 connected to mass M1, and the mass M1 is connected to truss of length L2, which is connected to mass M2. The inclination angle of truss M1 we define as θ1. Inclination angle of mass of truss 2 we define as θ2. So let's first derive the Euler-Lagrange equations. First we rewrite coordinates x1 and x2, the coordinates of mass M1, in terms of L1 and θ1. So we can write x1 as L1 times sine θ1, and y1 will be minus L1 times cosine θ1. We do the same for the coordinates of mass M2, coordinates x2 and y2. Here, however, x2 will be x1 plus the length which is contributed by the truss 2. It will be L2 times sine θ2, and inserting x1 here, we obtain this expression. And y2 will be the same. We've got y1 and plus the contribution in y direction from truss L2. It will be minus L2 times cosine θ2. Inserting y1 here, we obtain this expression. So now we find the time derivatives x1 dot and y1 dot. Here, variable depending on time will be only θ1. Do the same for x2 and y2. Find x2 dot and y2 dot. So the calculation will be a bit lengthy. That's why we need a symbolic calculation. So let's import a package for that. And we have to define our parameters, which we have length L1, mass M1, length L2, mass M2, and we have time t and gravitational acceleration g. And we've got also θ1 and θ2, which will be defined as functions because they are the functions of time t. And we add this line to allow the printing, to enable the printing. Then the kinetic energy of the system can be found as the sum of kinetic energies of both of the masses. So it will be 0.5 mass m1 times velocity of mass 1, which has again two parts in x and y direction. It will be x1 dot and y1 dot, and the same for the mass number 2, 0.5 times mass 2 times velocity of the mass 2 squared. So inserting x1 dot, y1 dot, xy to y2 dot here, we obtain this expression. So now we define the kinetic energy T. It's a very lengthy expression. L1 squared. So our kinetic energy T will be such a lengthy long expression, and we see here that θ1 is as I mentioned before, it's a function of time t, and θ1 dot will be written like θ1 dot div t. It means we take the derivative of θ1 with respect to time t, and the same is for θ2. Now the potential energy V can be written as m1 plus m2 gy2, and then inserting in y1 and y2 here, we obtain this expression. So this is our expression, and again we see θ1 is a function of t, and θ2 is a function of time t. Lagrangian can be written as t minus v. And since we have 2 degrees of freedom, we have system of equations here, where in the first equation we take derivative with respect to q1 dot and q1, and in the second equation we take derivative with respect to q2 dot and q2, where q1 is θ1 and q2 is θ2. So now let's see how the first equation will look like. So write derivative of θ1 as a function of t with respect to t, and we have to take a derivative of L with respect to θ1 dot. With respect to this guy, and then we have to take time derivative of this guy with respect to time. So write diff with respect to time, and minus derivative of L with respect to θ1. And this is all equal to 0, so we write equal to 0 and run. So this is how our first equation will look like, and we can do the same for the second equation. Here we just replace θ1 by θ2, run. So that's our second equation, and the whole system, our Euler-Lagrange equations in terms of θ1 and θ2 will be looking like that. Very, very complex. So now we'd like to solve these ordinary differential equations. Again, we first import the required packages, import NumPy, and the package for solving the ordinary differential equations. First, we have to convert our second order differential equations into first order equations, and for that purpose we have to replace θ1 by ω1, by the angular velocity one, and θ1 dot dot by ω1 dot, θ2 dot by ω2, and θ2 dot dot by ω2 dot. So basically we have to make such replacement, and we have to bring this time derivatives of our variables θ1, ω1, θ2, ω2 on the left hand side. So now we have to define some variables needed for symbolic computation. It will be ω1, ω2, ω.1 and ω.2. So now we have to perform the following substitution. This can be done in the following way. We take first the first equation, we take the left hand side of it, and then we substitute a second derivative of θ1 with respect to ω.1 by ω.1, and second derivative of θ2 with respect to time by ω.2, and the first derivative of θ1 with respect to time by ω1, and first derivative of θ2 with respect to time by omega 2. And we do the same for the second equation. So that's how we perform the substitution in equation number 2. And now we have to bring omega dot 1, omega dot 2 on the left hand side. So it means we have to express omega dot 1 and omega dot 2 as function of theta 1, theta 2, omega 1 and omega 2. In order to do it, we write the following. Run. Calculation is finished, so this is omega dot 1, this long expression, and this is omega dot 2. So now we can solve these ordinary differential equations of the first order in order to obtain the motion behavior. First of all, we define again, like in the previous exercises, for the pendulum. So now it's basically the same what we did in previous exercises. We have our vector variables y, where we have theta 1, omega 1, theta 2, omega 2, and omega dot 1 is this lengthy expression over here, omega dot 2 is this lengthy expression here, and then we define the time derivative of y as omega 1 dot, omega 2, omega 2 dot. We have to define the parameters. Length 1 is equal to 1, m1, length 2, mass 2, g, and now we define the initial conditions, our vector y 0. So we have here 4 components, theta 1, omega 1, theta 2, omega 2. We can assume that theta 1, theta 2 are initially 0 and set only the values for theta 1 and theta 2. So theta 1 can be pi over 2, omega 1 is 0, theta 2 can be, I don't know, pi, omega 2 is also 0. So now we define the time domain as in previous exercises, t, using function in space from 0 till 30, and we need 3000 nodes. And solve the system of differential equations using the imported package. After the calculation is finished, we can plot the results. And here we see the animation, where the blue point is mass number 1, the red point is mass number 2. We see such a sophisticated movement. This GIF is created using PNG files, and I'll not be giving it here. I'll leave it for you. You can do it if you want. I'll just mention that you can under this link you can find the code for creating PNG files, which you can then transform into such GIF.